In this video, I'll be teaching you how to derive Michaelis-Menten equation. In an enzyme catalyzed reaction, an enzyme binds to a substrate, forming an enzyme-substrate complex, which dissociates, releasing the product and regenerating the enzyme. Here, K1 is the rate constant for formation of the enzyme-substrate complex. K2 is the rate constant for dissociation or breakdown of the enzyme-substrate complex into the free enzyme and substrate. K3 is the rate constant for product formation. To proceed, is a key concept when deriving Michaelis-Menten equation you need to be familiar with, and this is called the steady-state assumption. This assumption is of the idea that the concentration of the enzyme-substrate complex remains relatively constant over time. That is, the rate of change of the concentration of the enzyme-substrate complex with respect to time is approximately zero. In other words, the rate of formation of the enzyme-substrate complex is equal to the rate of breakdown of the enzyme-substrate complex. We know that K1 is the rate constant for the enzyme-substrate formation. Therefore, the rate of formation of the enzyme-substrate complex would be K1 times concentration of the enzyme times concentration of the substrate. We also know that K2 is the rate constant for the breakdown of the enzyme-substrate complex, and K3 is the rate constant for product formation, that is, the dissociation of the enzyme-substrate complex. So, the rate of breakdown of the enzyme-substrate complex would be K2 times concentration of the enzyme-substrate complex plus K3 times concentration of the enzyme-substrate complex. Factorizing ES on the right-hand side of the equation, we have this. Now, when we rearrange this equation, we have concentration of the enzyme times concentration of the substrate over concentration of the enzyme substrate complex is equal to K2 plus K3 over K1. What we simply did here was to bring this K1 down and also bring the ES down. Now, let's take this as our equation 1. This K2 plus K3 over K1 is equal to Km, which is Michaelis constant. So, in this equation 1, we replace K2 plus K3 over K1 with Km, which is Michaelis constant. Doing that, we have Km, which is Michaelis constant, is equal to concentration of the enzyme times concentration of the substrate over concentration of the enzyme substrate complex. To continue deriving this equation, we need to be familiar with a term known as the total enzyme concentration. The total enzyme concentration is the sum of the concentration of the free enzyme and the enzyme substrate complex. Now, we make the enzyme concentration the subject of this equation and then substitute it into equation 2. When we substitute this into equation 2, we have this. Next, we cross multiply, and while doing this, we remove the bracket by multiplying the total enzyme concentration and the enzyme substrate concentration by the substrate concentration. Doing this, we have this. Collecting like terms with respect to ES, we have this. Now, factorizing ES on the left hand side of the equation, we have this. Now, let's take this as our equation 3. From Michaelis-Menten model of kinetics, we have that the reaction rate V is equal to K3 times concentration of the enzyme substrate complex. Making the concentration of the enzyme substrate complex the subject of this equation, we have this. Also, we have that the maximum reaction rate is equal to K3 times the total enzyme concentration, making the total enzyme concentration the subject of this equation. We have this. Now, we substitute Es as V over K3 and Et as V mass over K3 into equation 3. Doing this, we have this. Multiplying both sides of the equation by K3, we have this. Now, making V subject of this equation, we have V is equal to V max times concentration of the substrate over Km plus concentration of the substrate. And this equation is known as Michaelis-Menten equation. If you watch this video to the end, drop a comment, like, and most importantly, don't forget to subscribe.